Welcome back to AI.Code.Cast. I'm so excited for today's deep dive. We're going to be tackling a really fun coding challenge, and it really gets at the heart of, well, how can we be clever with the way we write our code? So it's great if you're prepping for like a technical interview or just want to sharpen your skills.
Yeah, I love these sorts of problems. They really make you think outside the box, and it's not just about getting the right answer, but like how do you get there efficiently?
Exactly. So today's problem, it's called longest repeating character replacement. Sounds kind of intimidating, but trust me, the concept is pretty intuitive. Imagine you've got like a string of letters, just random, like A Bible, something like that.
Okay, I'm picturing it. Yeah,
Now, the challenge is we're allowed to swap out some of those letters,
yeah,
right? But there's a limit. Let's say for this example, we can only change one letter.
gotcha. So kind of like we're tweaking the string a bit to see what we can make.
Exactly. And the goal is to create the longest possible stretch of a single repeating character. So with A Baba and just one replacement, what's the longest run we can get?
Hmm. Well, if we swap out that lone A in the middle, we could get A B B B B A. So that's four repeating B's.
You nailed it. That's exactly right. But of course, we want more than just the answer for this one specific case, right? We're after an algorithm, like a set of instructions that can solve this for ANI string no matter how long or messy, and any number of allowed replacements.
Yeah, that's where it gets interesting. Going from a specific solution to a general one. That's the heart of algorithm design.
Absolutely. It's like having this magic wand that can rearrange letters and always find the longest repeating pattern no matter what you throw at it.
Hmm.
So let's start with like the most obvious approach, even if it's not the best one. How would we tackle this with brute force? Just like the simplest way you can think of.
Okay, so brute force. Well, we'd basically have to check every single substring within our string, right? Like we'd look at AA, then AAB, then AABA, and so on. For each of those, we'd count up how many times each letter appears and see if we can make it all the same letter using our allowed replacements.
Yeah, okay. I see where you're going with this, but it feels like that would get out of hand really quickly, especially if the string is super long.
Exactly. It's like trying to find a needle in a haystack by examining every single piece of hay. And it's not just a little inefficient, it gets exponentially worse the longer the string is. We call this exponential time complexity, and it's something we generally try to avoid like the plague when we design algorithms.
Okay, so brute force is out. There has to be a smarter way to do this. Any hints you can give us
Yeah.
to kind of nudge us in the right direction? Like what sort of thought process should we be having?
Okay, so think about how you might approach this problem manually. If you were scanning the string with your eyes, like on a piece of paper, would you be constantly going back and revisiting previous parts of the string? Or would you try to move forward in some kind of systematic way?
Hmm, that's an interesting point. I think I'd naturally want to keep moving forward, right? Like focus on a specific part of the string at a time, figure it out, and then shift my attention further down the line, almost like I'm using a sliding window.
Bingo! You've hit the nail on the head. The
Well,
sliding window technique is super powerful for these kinds of problems because it lets us process the string in a linear fashion and avoid all that unnecessary backtracking.
okay, now I'm intrigued. Tell me more about this sliding window magic. How does it actually work?
All right, welcome back to AI.Code.Cast. So we're getting into the thick of it with this longest repeating character replacement challenge, and we realized brute force is just not going to cut it. Way too slow. But you had that great insight about a sliding window being a possible solution, right?
Yeah. I'm still kind of fuzzy on the specifics, though. Like, I get the general idea, focus on one part of the string at a time, then move that window along. But how does that actually help us find the longest repeating sequence? And how do you even represent a window in code?
Awesome questions. Let's think about it this way. Imagine you've got two pointers. Let's call them start and end. These are like the edges of our window.
Okay, I'm picturing it.
So at the very beginning, both of these pointers are pointing to the beginning of the string, meaning our window is, well, empty at the start.
So we're kind of just peeking at the string through this tiny window that's not really there yet, and then we gotta, like, make it wider, right?
Exactly. And we do that by moving the end pointer to the right, one character at a time.
Hmm.
So our window is expanding, and we're basically looking at a bigger and bigger chunk of the string. Now, as we go along, we need to keep track of how many times each letter occurs within that window, almost like we're keeping a tally or a score for each letter.
Ah, okay, that's where that frequency map thing comes in, right?
Mm.
It's just a fancy way of saying, hey, let's count how many times each letter shows up.
Spot on. Now, here comes the really important part, okay? Every time we expand our window, we need to check if it's still valid.
Hold on, valid. What does that mean in this context? Like, how can a bunch of letters in a window be invalid?
Well, a valid window means it's still possible for us to make all the characters within that window the same by using our allowed replacements. Don't forget, we have that K value from the problem that limits how many swaps we can make.
Right, right. Okay, so if our window has, let's say, 5 characters, but the most frequent letter only appears twice, we know we can't turn that into a repeating sequence with only one replacement, for example.
Mm-hmm.
We'd need more swaps than we're allowed.
You got it. That's exactly what the validity check is doing. It's like making sure we're not wasting time on windows that just can't work. Now, think about how we'd actually implement this check in our algorithm. Any ideas? What info do we need?
Well, we know the size of the window. That's just n minus start, right? And then we also need to know how many times the most frequent letter shows up within the window.
You're right on track. We can get that info straight from our frequency map. It's basically the highest score on our scoreboard. Maybe we call it max frequency just so it's super clear what we mean.
Okay, I think I see where this is going. If we take the window size and we subtract that max frequency, and if that difference is greater than k, our allowed replacements, then the windows is invalid, because it means we've got too many characters that need swapping to make them all the same.
Boom! You absolutely nailed it. You've cracked the code of the validity check. Now, what do we do when the window is valid? What's our main goal here? Think back to the problem.
We want the longest repeating sequence possible, right?
Right.
So if the window's valid, its size is like a contender for our longest so far, right? We got to keep track of the maximum window size we've seen during this whole sliding process.
Perfect. That's exactly it. We're keeping track of the best we've seen. Now think about this. What if our window becomes invalid? What do? Throw in the towel.
Meh. There's got to be a way to keep moving forward, right? Instead of shrinking the window back down, what if we just slid it forward? Like move both the start and the end pointers one step to the right. Keep exploring.
Now you're thinking like a true algorithm master. That is the essence of the optimized sliding window technique, my friend. We never backtrack. We only slide forward, constantly exploring new possibilities as we go. But there's one tiny detail, one tiny adjustment we got to make when we shift the window like this. Any guesses?
Well, we're moving the window, so wait a minute. We need to update our frequency map.
Yeah.
Because the character that just left the window, its count needs to go down, and the new character that just entered, well, its count has to go up, right?
You got it. You are on fire today. By keeping our frequency map updated and constantly checking if the window is valid, we can make this window glide across the entire string, no problem. And as it slides, it reveals the longest repeating sequence, kind of like a treasure hunter uncovering hidden gems.
This is amazing. I love how, like, this one simple idea, this sliding window, can make things so much more efficient. But we've been talking about it conceptually. How do we actually make this into something a computer can understand? What does the code for this look like in a general sense?
Great question. We won't write out actual code here, line by line, but we can definitely outline the steps, the logic, in a way that any programmer could translate into their favorite language.
Welcome back to AI.Code.Cast. It's been quite a journey these past 2 parts, really digging into this whole longest repeating character replacement thing. We started off with brute force, kind of cringed at how slow it was. The light bulb moment, the sliding window idea, just so elegant.
Yeah, and we even sketched out like the step-by-step logic of how the algorithm works. But I think it's worth like zooming out a bit now, thinking about why this sliding window is such a big deal in the wider world of coding.
Right. I mean, it's clearly a slick solution for this string problem, but my hunch is its uses go way beyond just letters and words.
Absolutely. Think of it this way. Anytime you've got data that's in some kind of sequence, right? Could be numbers, sensor readings over time, anything. The sliding window lets you analyze chunks of that data efficiently.
So instead of looking at the whole massive thing at once, which can be overwhelming, we're saying, okay, let's focus on this bit right here, get what we need from it, then slide our focus over a bit.
Exactly. It's kind of like reading a book, You don't try to absorb the whole thing in one go. You take it paragraph by paragraph, building up understanding as you go.
Yeah.
The window is like that focused attention.
And by sliding it, we're kind of reusing some of the knowledge from the previous chunk, right? We don't have to completely recalculate everything each time.
Exactly. It's that reuse that makes it so powerful. Imagine you're tracking the average temperature over a week, right? The sliding window lets you update that average day by day without starting from scratch each time.
So it's not just about finding the longest of something. It's really a general way to analyze any kind of sequence while still making sure it meets some condition, like our key replacements rule from earlier.
You got it. Have you ever come across the longest substring without repeating characters problem? Classic interview question.
Vaguely, yeah. Rings a bell. Something about finding the longest part of a string where all the letters are unique, right?
Yep, that's the one. And guess what? Sliding window is perfect for that too. The window becomes like our tool for enforcing that uniqueness rule. If we hit a repeating letter as we expand, we just slide the window over enough to get rid of it.
Ah, I see. So the window's like a filter, making sure that at any given time, we're only looking at data that fits our criteria. That's so
Yes.
cool.
And the best part, that core logic, it's so adaptable. Finding substrings with a specific sum, spotting patterns and stock prices, you name it, the possibilities are huge.
This has been awesome. We went from this one specific challenge, dove deep into how the sliding window works, and now we're seeing how broadly useful this idea really is.
And hopefully everyone listening to AI.Code.Cast now feels like they could not only solve this one problem, but spot those sliding window moments in all sorts of coding situations. It's about that flexible thinking, not just memorizing solutions.
Couldn't have said it better. To everyone out there, keep those coding skills sharp, keep those minds open, and until next time, happy coding.